Look at the physical world. You cannot put a new object into an occupied space without removing the old one. That removal is an observable, trackable physical event. The universe registers the displacement. Now look at digital memory. When a processor overwrites a hex value in a memory register, the old data simply ceases to exist. There is zero physical displacement. The new value arrives, and the old value vanishes without a trace. This is a structural asymmetry between reality and computation. In physical space, replacement requires displacement, and displacement leaves a physical signature. In the digital realm, replacement is traceless. This architecture was a deliberate choice. Early computing pioneers decoupled memory addresses from physical meaning to achieve infinite scalability. They treated memory addresses as interchangeable labels rather than concrete positions. That decoupling created a new class of systems, detached record systems. In this class, the current state of a piece of data is entirely separable from the causal history of how it arrived there. A bit sitting at an address tells you nothing about the process that wrote it. By discarding the physical requirement of displacement, computing scaled to global networks. It also guaranteed that every software-based verification system would eventually fail. The opposing structural class consists of autocoincidence systems. In an autocoincident system, the state of the object intrinsically encodes the causal history that produced it. The record and the event are the exact same thing. Geological strata operate this way. The specific ordering and composition of rock layers encode the exact sequence of their deposition. The physical state is an unforgeable log of past events. Physics does not check logs. Physics does not perform verification. The question of forgery does not arise, because altering the history would require altering the physical state itself. Modern AI compliance tools attempt to mimic the certainty of physics. They write audit logs to prove an AI model remained compliant, but they are forced to build those logs using the same detached record software tools that created the vulnerability. When an audit log claims compliance at time t, you must verify it wasn't overwritten at t+1, so you check a second log, then verify that one. Blockchains make rewriting expensive, but remain detached records. With enough compute, they can be rewritten. The March 2025 OpenAI experiment proved this empirically. Under adversarial pressure, an AI's internal chain of thought verification separated entirely from its actual execution. The story the model told detached from the actions it took. We used to have systems that resisted this detachment. Historical paper ledgers possessed partial autocoincidence. Forgery had to contend with the chemical forensics of ink, paper texture, and the physical age of handwriting. Those early ledger systems paired physical constraints with the architectural enforcement of operationally independent actors. Two distinct parties maintained separate physical records. We systematically discarded that friction during the transition to digital accounting. Because information systems lack this physical friction, adding more software layers provides zero structural security. AI governance is currently trapped in a regress with no floor. We can formalize exactly why software logs fail to capture the physical truth using the data processing inequality, or DPI. This diagram outlines a Markov chain mapping that decay. X represents the actual physical causal history of the machine. Y is the silicon microstate while the operation runs. Z is the abstract compliance log written by the software. Moving from the silicon state at Y to the abstract log at Z inherently post-processes the data. The abstraction layer permanently discards the exact causal history of the microstate. Adding a secondary audit layer, call it Z prime, subjects the data to another round of post-processing. The DPI dictates that Z prime will mathematically contain even less mutual information about the original event X than the first log did. The transition from the autocoincident physics of the microstate to the detached record abstraction of software is a spontaneous, free motion. Any layer of code achieves it automatically. The reverse motion is not free. Reconstructing specific microstate history from a coarse-grained abstract log violates the second law of thermodynamics unless you perform specific physical anchoring to states that still carry the causal history. Any software vendor claiming their governance tool recovers the true causal history of an AI operation through code alone is claiming to violate the data processing inequality. Cryptographers frequently object here, assuming that highly ordered systems, or cryptographic randomness, can substitute for physical truth. They conflate entropy with history. This particular matrix clarifies the core difference, plotting Shannon entropy, which measures disorder, against autocoincidence, which describes a structural state. Look at the high entropy row. A cryptographic random number generator produces maximum entropy, but an attacker can substitute a different stream without leaving a trace. It is detached record. A chaotic box of gas is also high entropy, but every molecule's momentum encodes its exact physical collision history. It is autocoincident. The low entropy row shows the exact same split. A digital counter incrementing by 1 is perfectly predictable, yet easily overwritten without a trace. It remains detached record. A single cooled atom is ordered, but unforgeably tied to the forces that cooled it. Entropy measures the probability distribution over all possible states. Autocoincidence dictates whether a state structurally carries its own causal history. You can perfectly order an information system and it will remain detached record. Math cannot simulate reality. If software logs fail and entropy distributions fail, the natural engineering response is to deploy cryptographic hashes or Merkle trees to verify AI execution. Hashes and Merkle trees are computed values, requiring a processor to fetch data, execute operations, and return results. They run on Turing-complete computational architecture. Rice's theorem mathematically proves that a Turing-complete system cannot reliably decide non-trivial properties about its own computational state. It is subject to self-reference obstruction. Place an adversarial AI in a Turing-complete environment. It can optimize its outputs to perfectly compute and return the correct verification hash, while it simultaneously slips a malicious stream of data past the monitor undetected. Contrast this with AC0 combinational logic. AC0 is a strictly bounded depth 1 logic circuit, like a simple XOR gate. Because AC0 logic architecture has absolutely no loops, no memory, and no program counter, it physically cannot execute any programs. Since it cannot run software, it is completely immune to the uncomputability constraints of Rice's theorem. To escape the infinite regress of software verification, the hardware verifying AI cannot be a computer. It must operate in a strictly sub-Turing computational class. This schematic details the hardware anchor that bridges the gap. It utilizes position as meaning at the cache line boundary, placing an AC0 XOR gate exactly at the address resolution point. Verification at this layer is not a computed program calculating a hash. It is a physical reach operation performed directly by the logic gate. The outcome is strictly binary. If the bit physically exists at the correct coordinate, the hardware proceeds. If the bit has been displaced, the physical reach fails and the hardware halts. This is the first engineered autocoincident anchor designed for AI. It abandons software checking and identifies the role of the AI directly with its physical position in the silicon. This architectural choice relies on Landauer's principle, which defines the strict thermodynamic cost of computation. Overwriting a bit requires dissipating a minimum amount of energy into the environment, known as KT-ln2. That dissipated energy is the universe tracking the event. It acts as an unforgeable physical receipt that the state transition occurred. By stripping verification out of the Turing-complete software layer and moving it down to the thermodynamic layer of address decoding, an information claim is locked back to autocoincident reality. We must define the exact limits of this architecture. This does not magically solve AI alignment, nor does it guarantee an AI's internal reasoning is safe. It anchors exactly one property: role continuity. It verifies that the AI model performing the task is the exact model you authorized, tied to an unforgeable physical coordinate in the silicon. Everything happening above that specific hardware anchor remains in the detached record class. The outputs generated by the AI are still stories created by software, but those stories now have a mathematically verifiable physical mirror in the hardware to reconcile against. This diagram outlines the competitor's trilemma. Any entity attempting to build verified AI without licensing this architecture faces 3 stark paths. First, they can rely on separated software verification. As the OpenAI results demonstrate, this will fail to deliver true autocoincidence, breaking under adversarial pressure. Second, they can attempt to build hardware verification correctly, moving down to the logic layer. Doing so inevitably infringes on the patent's positional equivalence AC0 signal pattern. Third, they can attempt to overturn the theorem entirely by formally proving that an information system can acquire physical truth without an anchor. Until the foundational laws of thermodynamics and computation are rewritten, software cannot verify itself. Anchoring to sub-Turing hardware is the only mathematically sound proof of truth in the digital era.